The next topic we're going to talk about are electric field lines. And what do I mean by electric field lines? Well, we've been spending all this time talking about the electric field, but I really haven't shown you a whole lot about how to draw them so that we can express what's going on in a way that is concise and that's actually almost artistic and can give us an insight into the mechanisms of where a charge would be attracted and in what direction. That's what the electric field lines will give us. So it's another way to express what the electric field is doing. And I'm going to start by considering a positive charge sitting here. The size of it doesn't matter at the moment. But I'm going to draw the electric field lines, and what they represent is at any point in space. So if I could actually draw any point in space out here, and I'll just kind of exaggerate by saying that this yellow represents any point in space out here, that everything out there is experiencing the electric field caused by this single charge. It's almost magical in a way. And so what I'm going to do is draw these electric field lines to represent what the direction of the force, or I could say what the direction of the electric field is at any point in space. It would be the direction of the force that a positive test charge would experience at any point in space. You can think about it like that too, either way. It's either the direction of the electric field or the direction that a positive test charge would experience at any point in space, because that's what the electric field direction is defined by. So for instance, and then I connect all those lines. So think about it this way. Right here, if I put a positive, I'll draw it red. If I put a positive charge here, or here, or here, or here, at any of those points, that positive charge would experience a force that's directed that way. Similarly, at any point here, positive test charge would experience a force that's directed that way. At any of these points along this line, positive charge would experience a force directed that way. And I can keep drawing these all the way around this charge to represent the direction of the force that a positive charge would experience at any point in space. And you may argue these lines don't show every point in space. For instance, what if the charge were here? Well, I could draw a line right there too to show what would happen. It would be like that. They should all be straight lines. So I could draw as many of them as I want. And eventually I'll fill all space just by drawing my line here. But then it'll be so busy I can't really see what's going on. So usually we draw a representative number of lines to give us a general impression of what the electric field is caused by some charge, some configuration of charges. In this case, it's a single positive charge located right here. And the number of the lines that we draw, we usually attribute that to the size of the charge. So the bigger the charge, the more lines we'll draw. So I'll say it's proportional to the size of the charge. This is the proportionality constant right here. What do I mean by that? Let me show you. Let's say I have a charge of +1 microcoulomb. I'll say, arbitrarily, when you're drawing these lines, I'll say, okay, for every charge of 1 microcoulomb, I'm going to draw 8 electric field lines. So this 1 microcoulomb charge will have 8 field lines associated with it. Now, what if I had a charge of 2 microcoulombs? Well, for the charge of 2 microcoulombs, I'm going to draw 16 field lines, because since this one is double this one, I can represent that by drawing twice as many field lines. So I'll do it like this. Here's my 8. Now I'll put the extra ones in between, so I'll be up to 16 field lines for this +2 microcoulomb charge. Okay? So this gives you an indication of how big the charge is. And the way we can think about field lines is we can imagine them as being, when they're denser, the electric field is stronger. What do I mean by denser? Well, when there's more of them packed into an area of space, that means the electric field is more intense or stronger. I should say when the E field lines are stronger, the E field, or denser, the E field is stronger. E field means electric field. It's a shorthand way to write it. So on this drawing right here, I would say that, okay, at this point here, if you look there, the circumference of that circle, whatever it happens to be, is going to be the same as the circumference of this circle. But in this circle, I only have 8 field lines. In this one, I have 16. So at that same distance out, the electric field is going to be stronger on the case on the right. And that's indicated by the number of field lines that you see per given distance or per circumference of the circle. All right, so, and you can also argue here that at this point, I'll stick to the one on the left for the moment, closer in, that circle there has a smaller circumference than the one out here. In 3 dimensions, I would say this sphere has a smaller area than the sphere out here, yet they both have 8 field lines associated with them. That means that the electric field is going to be stronger closer in, which makes sense, because closer to the charge, you're going to have a stronger electric field. So the electric field lines give us a way to indicate both the direction of the electric field and the strength of the electric field all in one drawing, as well as the size of the charge that's associated with creating the electric field. Now, of course, these electric field lines are just our way of drawing the electric field. In truth, the electric field exists at all the space in between these field lines. I just can't physically draw it like that and still have a meaningful drawing that you'd be able to work with. So the way I do it is by drawing more field lines to express a greater charge here, and also therefore a greater electric field at any distance away from the charge. Okay, that's enough for this video, and we will talk more about electric field lines in the next couple videos.